So, we got a significant result here, and we can write it out in APA way, but we don't know which groups are different. It looks like kind of group 1 is probably not that different than group 2, correct? Looks like both groups are different than group 3, so whenever you get an analysis, it's always good to look at things, and then we got a little dilemma here. So, if we wanted to figure out which groups are different, what could we do? We could just do t-tests, right?
Okay.
We could just compare group 1 to 2, 2 to 3, 1 to 3. But does that seem to make sense here? Somewhat, but not really totally. There's a big problem with doing t-tests after ANOVA. And this is a real important one to write down. The big problem is that if you have lots of groups, let's say it's not just 3 groups, but you have 1 independent variable and 5 groups, that's going to be a lot of t-tests. That the more t-tests you run, you're going to actually start getting significant results when it was actually due to chance. You're going to start getting significant results that were actually just due to chance. Just because if you run 50 t-tests, 5 of them might be significant just due to chance. Do you remember what we call that kind of mistake? Where you say, oh, these are significant, there's really effects here, but there was nothing there.
That's a type 1 here?
That's a type 1. It's a false alarm. It's a false alarm error. And do you think statisticians want to make these false alarm errors?
No.
No. So if you find a significant ANOVA, it's not considered appropriate to do t-tests after them to see the differences. We want to stop this, and it's given a particular name, and it's somewhere in your book there as well. I think I wrote it down somewhere. It's called a family-wise type 1 error. Did I write that in there somewhere? I thought I did. It's called a family-wise type 1 error. No, I thought I did. Oh, there it is. 416 to 419.
Family.
It's called a family-wise type 1 error. The problem we have is that if we just do a lot of these t-tests after a significant ANOVA, the problem is you're going to tend to get significant results that were just type 1 errors. It's called a family-wise type 1 error, and we don't want that to happen. Doing t-tests after ANOVAs, if you do an ANOVA and then follow it up with a t-test, that's actually called a post hoc kind of test. It's after the fact. So what we're going to learn about today, as kind of our last big deal, is what we do compute after we get a significant ANOVA with more than 2 levels. What we actually run are things called post hoc tests. Are you all right, Em?
I'm just really tired.
That's okay. We're going to learn about these things called post hoc tests. To make a long story very short, a post hoc test is kind of like a t-test, but it is simply more conservative. It's more conservative. It cuts down on this family-wise type 1 error. So if we get a significant ANOVA, we run a post hoc test. And we're only going to, it's a conservative thing. It's got to be, it's much more conservative than a t-test. You really got to have a big difference between the groups to be significant. You didn't take your medicines?
No, I forgot to submit the assignment.
That's okay. You can do it after class. I think I know the instructor. So,
will it be counted as late?
Don't worry about it. So,
I asked you a question.
no, I have plenty of males in the class who have yet to submit. So don't worry about it. So the idea is that we need to do a post hoc test. So let's actually do this by demonstration. Go into Analyze again. Go into Compare Means.
Oh, I should use
Nope, you're fine either way. Compare Means. And go into One-Way ANOVA again. And now you've got the descriptives there. Look at that button on the right. Beverly, do you see the important button on the right?
Yes.
Post hoc. Let's click it on post hoc. Now it turns out there are about 20 different post hoc tests you can do. We're going to learn how to do one. I don't know, Beverly, did you do a post hoc test in your experimental class?
We did. We always used the Tukey's HSD.
Yeah, I always do the turkey test. Tukey was a famous statistician. Always around Thanksgiving, it's good to do a Tukey's test because, you know, Thanksgiving, turkey. Fisher, Tukey, these are all famous people. So we're going to learn how to do the Tukey's test. So click it on Tukey's and do continue. You don't need to know the other ones. Other people have other ways. Do continue. And now click it on OK. And now you have a big printout that should be very parallel to what I gave you. Well, it took a lot of work to get this on 3 pages. I really had to work hard. So let's take it from the top of our menu here. Under B here, we got the one way. How many independent variables here?
3.
1.
Is there one independent variable in 3 levels, or are there 3 independent variables?
1 independent.
Yeah. You always got to say, if there are 3 independent variables, what are the levels for each one? My dissertation had 3 independent variables, and that was a mess. But I still got it statistically significant to move out to Rockford, Illinois. So that was good. But this is, you're not going to get 3 factors from me. 1 independent variable, 3 levels, contact, bumped, and smashed. Dependent variable is speed estimate. Does it look like from the descriptives that we might have something there? As you eyeball it, did the descriptives look good for a significant effect? Beverly, what do you think? Did the descriptives look good for a significant effect?
Especially between the smashed and the other group.
Yeah, it looks like this. Yeah, exactly. It looks like between the smashed and the other 2 groups, maybe not between the other 2 groups. If you really wanted to do the math, but you're not going to, for me, you get the group means, 29, 32, 51, minus the 37, quantity squared, times 3 in each, add them up, and you get, what would you get if you did all that math? You'd get 854. So the answer is there. You want that number to be what? Large. So you get 854. The 854 in the ANOVA screen is the treatment effect. You want that number to be large. Is that large, Alexis?
Yes.
Yes. How do you get DF2 there? Emily, how do you get DF2 on that ANOVA table? How do you get DF2?
Oh,
because you have 3 separate groups. And
3 groups?
1.
So it's 3 groups minus 1. Degrees of freedom. You got 3 groups. It's between group variance. 3 minus 1 is 2. And then how do you get the variance between groups?
Because you do 3 minus 1, 3 minus 1.
Nope. Variance between groups was the question.
Oh.
Sums of squares between groups, 854. Degrees of freedom between groups, 2. Divide them. It's very important when you're doing these things out by hand, write all the terms you get and what they mean. Because it's very easy to, wait, what's this, what's that, and then you screw one up and then it costs you a bunch. So when you're doing, you will do on the test a 1-factor ANOVA, 2 levels. Make sure you write out sums of squares, and if you type it out, that's fine. I don't need all the right symbols, but just make sure you say this is this, because you don't want to get it messed up. Beverly, is this working for you? Okay, so sums of squares within group at 18. Do we want that number to be large or small, Beverly?
We want it to be large.
Sums of squares within group.
Oh no, we want it to be small because it's on the denominator.
Yep, we want that to be small. That reflects error. 18 is a very small number because the numbers are very close.
Flip-flops, not me.
Yeah, if you look at the numbers here for smashed, 50, 51, 52, the sums of squares there are 2. If you have numbers, and you may actually want to know this, that if you have numbers where the dispersion is by 2s, The sums of squares, if it's 27, 29, and 31, is always 8. So you got 8 there, 8 for 30, 32, 34, 8, 8 plus 2, that's 18. So that's good, that's 18. How do you get degrees of freedom 6, Beverly?
It's the
3 minus 1, 3 minus 1.
Alexis has got you here.
Yeah.
You have 3 people in the first group, 2 there, 3 people in the second group, 2 there, 3 people in the third group, 2 there, and 6. You can actually look in the descriptives for n, see 3, 3, and 3, and go 2, 2, and 2. So 6 there. How do you get the variance within group?
18 divided by 6.
There you go. 18 divided by 6 is 3. F is 142. Sig is 0, 0, 0. You'd write P less than 0.001. Statistically significant. On the test, you could get, you're not going to be asked to do any SPSS analysis, but you will get output screens. And I will expect that if you get an output screen with simple means, like 3 consecutive numbers or even numbers that are 2 apart, that you will be able to know, like sums of squares is 2 and where you get the numbers from and what it all means. Interpretation of printouts is going to be a big part of the test. Okay?
Now let me ask you, anytime
Yeah.
you're writing an APA for an F score, you're always having the numerator and the denominator.
Yep, if it's
for
an
your
F.
degrees of freedom.
That's right. If it's
Okay.
an F test, because it's the numerator and the denominator.
Okay.
So you always have the 2 and 6, or the 1 and 4 is more regular for us. So we have a statistically significant effect, but we don't know where the effect is located. If we look in the 2 keys test, take a look at this. Actually, a good time to stop.